So there's no homework due, but there will be a new homework assigned at the end of the class. Tools, I got nothing for you this morning. Because instead I wanted to talk about real and protected mode on the x86. So let's do a short dive into that. So some of you may already know what this is all about. Some of you may not. It's kind of worth discussing because it has an impact on some embedded systems. It can have an impact on your BIOS and on a few other places as well. So the x86 CPU operates in one of two modes. It operates in real mode or protected mode. And real mode seems like what it should usually be doing, but it's not. Real mode is very limited, and it's the basically when your processor is running in real mode, it's essentially a really fast 8086. That's basically what it is. So an address in real mode is an actual physical address. There's not virtual memory in real mode. You just directly access memory, and you're limited to a 20-bit address space. And so if you do the math on that, you'll figure out that's about a megabyte or a MB according to the new standards, a MB. And that should be enough for anyone, right? That's more than 640K. So that should really be enough for anybody. You can, in fact, play both Doom and Crisis in a MB, so that should be plenty. Addressing is done using 16-bit registers. Well, wait, you might say, 16 bits is not 20 bits. How do I get a complete address? Well, that's where segment registers finally come into play. A 16-bit segment register is combined with a 16-bit offset register. And you may say, well, wait, that's 32 bits. Why is it just 20? Well, again, the segment register is shifted left by 4 bits, and then the offset register is added to it. So if you take the 16-bit register, you shift it left 4 bits, you have a 20-bit address space that you can address. And the fun part about this is that you can address a single location in multiple different ways. If you think about this for a few minutes, right? Because I can subtract 32 from my segment register and add the 32 to the offset, and I can play these kinds of games, and I can address memory in multiple ways. Oh, it was a crazy time. So the segment registers, you probably already know about. There's a code segment, a data segment, the stack segment, and then the extra segment. And then there's lots of 16-bit, the usual 16-bit registers, the instruction pointer, the stack pointer, ABCD registers, and the destination and source registers. That's mostly true, but it's not the full story. So you might go and look up something that was called Unreal Mode. So Unreal Mode used a trick that used the fact that you could switch a processor into protected mode, which we'll talk about in a moment, and use some of the resources in protected mode and then flip back into real mode. And because you've done this switch, the processor would continue to use some of those resources, and you could trick it into letting you access a larger range, typically about 4 gig. And if anyone is old enough to remember HighMem.sys, if you lived in the 90s and were paying a lot of attention to these things, that's how it worked. It's also the case that the 286 and later processors actually had more address lines. They didn't just have 20 address lines, A0 through A19. They had more. They had 32 address lines. So if you think about the segment and offset addressing, you might ask, well, what happens if I put the maximum value in a segment register, right? Over here, this FFFF, right? And I multiply it by 16 and I get this, FFFF0. And that's the right number of bits, right? Each of these characters is 4 bits. So that's 4 times 5, which is 20 bits. That's my 1 MB address space. And okay, that seems reasonable. And now I add an offset. Well, the offset is also 4 of these characters. And so I could, in fact, overflow that space pretty easily. Now, in an 8086, what happens is when I overflow that space, I only have 20 address lines. I can't magically address something that's above that. I basically just do modulo 2 to the 20th. But on the 286 and later, there actually are those higher address lines. In particular, there's address line 20, right? 0 through 19 were the original 20 lines. A20 refers to the 20th address line, the 21st, since we're starting from 0. And it exists. And so what happens when you overflow is you actually get to use that extra address line. And so that was also a trick to let you access some memory beyond that 1 MB limit, which really, since it's more than 640K, should have been enough for everybody. Apparently, it wasn't. Okay, and there was the decision was made. It wasn't an accident. This was a conscious decision when they were designing the 286 to say, you know what, we'll just let that work. So, not something you need necessarily to know that much. Protected mode is where the interesting and exciting things start. It's where the real chaos begins. Up till now, you've had a machine that did more or less what it was told. It had some quirks, certainly, but memory was memory. If you wrote to memory, you pretty much writing straight to memory. Cache was a fairly primitive affair, and a lot of things were fairly simple. Protected mode tried to preserve the illusion that all those things were still true, while bringing in a whole raft of other things that are good, but that begin to separate you a little more in the programming model from the actual physical hardware. The most important thing is probably the idea of virtual memory. So 286 had a protected mode. It's not the same as what's in the 386 and later. So when you think about protected mode and you read that 286 had it was different. I'm trying to think of a machine that used the 286. The IBM PS250, I think, used a 286 and ran some version of DOS and possibly OS2 that made use of that. But for the most part, the 286 is this weird anomaly. It's not the 8086, so it's not that simple model, and it's not the 8386, so protected mode doesn't work the way you expect, so it's kind of forgotten. And it'd be hard to find a working 286 machine, and I think probably impossible to get a Linux or something like that running on it. So virtual memory is a big deal. Virtual memory says that I can now separate my view of memory from the actual physical memory, and that's a really important thing. That means that I'm able to do some really neat tricks, like I can have multiple programs that each appear to have their own independent address space. That's kind of cool. I can, if I have location independent code, then a position independent code, I can map libraries into memory, and they'll occupy some space in physical memory, and then I can map those same pages of memory into multiple different process spaces. And so I don't use 10 times the space. I only use that space once, but I'm able to map it across all of them. And that works because, again, I have virtual memory. Virtual memory is not a new invention of the 80s. Virtual memory had been around a long time at this point, but bringing it into these fairly inexpensive home computers was really a major transformation. We also had a larger address space, right? We had 32 bits of address space. 32 bits can address 4 gigabytes. That should be enough for anybody, right? I think we can all agree that's enough for anyone, right? The benchmark is, can I install Linux, play Crysis, and play Doom? And if those things are true, then you clearly have a sufficient computer to get the job done. It also brought in multitasking is on the list. You could do multitasking in earlier processors. And in particular, Windows gave you a form of multitasking, but it tended to be cooperative multitasking. That is, you had to write your code with the explicit knowledge that there's going to be multitasking. So you have to turn over control. There were a whole series of ways in which you could make multitasking work on a fairly primitive processor. It was just not optimal. And if something went wrong with the program, you could still hang up the entire machine. And so with the 8386 and later, that got a lot better. There was now direct processor support for this, much better isolation of processes. And so that if your process wandered off into the weeds, it might go into the weeds, but the rest of the machine would hopefully keep running and doing what it's supposed to do. And memory protection, the one up at the top of the list. Memory protection was finally brought in, right? If I've got a flat memory model where an address is just an address, it's just an address, and I am writing directly into physical memory, I typically don't have memory protection. Some versions of VxWorks are like that today. They're basically very fancy versions of DOS, in a sense. And that means that if I am not careful with what I do, I can cause really bizarre behavior. Right? If I compute the wrong address, or I somehow get a wrong address in a register, and I jump to that location, or I try to write to that location, that will probably succeed. Instead of getting a general protection fault or a segmentation violation or these other things that stop me when I try to write into a space I shouldn't write into, or when I try to jump to code that's outside my own process, it will just work. And now I'm executing bytes somewhere, and who knows what's happening. And that's really problematic. Not on this list, but certainly of importance, is the idea of dealing with the fact that physical memory is often smaller than the actual address space. And why is that significant? Well, the processor doesn't know if you have, it doesn't necessarily know immediately, oh, you've got real memory here, and there's not memory in this address space, right? Think about let's think about a 64K address space. And let's assume that I've only installed 8K of RAM in that machine. So I've got 16 address lines, but I've only got 8K. I've got to decide where in that space to install it. Right? I probably have ROM in high mem. And so maybe I put my RAM in low memory, which means that if I choose an address above that 8K limit, the processor is going to put the bits on the address bus. They're going to go out, and I'm going to read something, but I'm not reading or communicating with memory at that point. And so I may just get, whatever stray signals happen to be on the data bus at that time. And then I'll try to execute those, right? So, but with one of the great benefits of virtual memory is I can set things up so that kind of foolishness just doesn't happen. All right. Lots of good, huge change in the way that the processor worked, the way you could write code, and a huge change in the complexity of the processor, obviously. So all these things require data structures to tell the processor, oh, what is privileged, what memory is privileged, what memory is protected. And because I have protection now, I have to bring in a notion of who can have access to protected areas. And so this is where I get rings, right? I get ring 0, where I run the kernel. I get ring 2, where I may run a lot of user code, and so on. That comes in here because now I need to have a way to deal with the fact that there's protection. So just imagine the degree of complexity, the change between the 8086 and the 8386 is huge. And it's not surprising that they tried once with the 286 and did not exactly get it right. And yes, I'm leaving out the 8186. Go read about it if you want to. It exists. It's a real thing. But really, 8086, 286, and 386 are the ones that sort of matter. So you have to set up these data structures to tell the processor, here's how memory gets mapped and how things work. And once you've done that, you can move your processor from real mode into protected mode. And then you're running in the modern way that this works. So what do? You set up the global descriptor table and the interrupt descriptor table. These are two really important tables that the machine starts up in real mode. And while you're in real mode, part of your job as starting up the operating system is to set up these tables and then do the long jump to trigger the switch to protected mode. These tables are located in physical memory, obviously, and because they're being set up in real mode, the registers that point to them contain real addresses, not virtual. They contain the real addresses. And there are two registers that we would deal with here. One is the GDT-R, which is the global descriptor table or register. The other is the IDT-R, the interrupt descriptor table register. And you can load them with the L versions of the LGT and LIDT instructions, and you can read them with the SGDT and SIDT instructions. And why aren't those? Why is it S? It's because you're either loading from memory into the register or storing from that register into memory. And these registers hold an 8-byte address that's in 64-bit mode, which is the one we care about, right? And in the 32-bit world, they would hold a 4-byte address. So they hold an 8-byte address in 64-bit world, and then a 2-byte length, so they can be up to 64K in length. So it's 10 bytes. These are 10-byte registers, and you load them up, and then you're able to make the switch over. And you can get their instructions. The load instructions are privileged. They will only work if you are in real mode where there's no protection, or you're in ring 0. Then you can use the load ones. But if you just want to get the addresses, you can do that. The store versions are not privileged instructions. In fact, let's see if I can. Do I have one? I guess I don't have one. There we go. So if you wanted to take a look at it, we could actually try to do that. So here's some little assembly code, and you might as well just give it a try. I reserved 10 bytes down here in the BSS section to hold the results. And then up here, I just do SGDT, and I store the results in data, which would be right down here. And then I exit. So how am I going to see the result of that since I immediately exit? Well, I'm going to run it in the debugger. Do that. And let's start up. So now we're about to execute the SGDT instruction. We've run it, and it should have stored its result in the buffer, and the buffer is at 402,000. So we can x/10bx, such a cryptic thing, 402,000. Let's see if that works, and it does. And so what we have here is a combination of the length and the address. And I believe the way this works, it's been a while since I've looked at this, so bear with me, is that that I believe these guys are the length, and the rest of this is the address. I think it's been a while. Could be backwards. I don't know. I haven't done this stuff in a pretty long time, but you can take a look at it, and you can read the documentation on SGDT like I should have before I did this, and you'll then know how that works. But it's something you can go and get. It's not a virtual address; it's an actual physical address. You can convert it over if you have the right, if you have the access to a page table that has that mapped, or you can modify it to map it. But basically, if you want to get access to the direct contents of it, you'll need to be in ring 0. All right, enough of that. What's in the global descriptor table? What's in there? Is there anything good in there? Something worthwhile? Should I be trying to hack the GDT? Well, in the 32-bit world, sure, go crazy. In the 64-bit world, maybe not as much. The global descriptor table defines segments, and it basically controls how logical addresses get translated into linear addresses or actual physical addresses. And the entries consist of a base, a size, and associated access privileges. We will talk way more about how addressing works later on. There's a whole, not today, but in a later class, I've got a whole section on computer memory because you need to know. And this all works just fine. In the 64-bit world, which is what we care about, the base and the limit are ignored. And you have 8-byte registers that cover an 8-byte address space. So it's 2 to the 64, and that's it. And so they're ignored. But does that mean this table is not used anymore, not relevant? No, this table still is relevant. You still have to set it up, and it's still used in some cases. And if you want to find out why it's used and how it's used, that's well beyond the scope of this class. But I've linked to the GDT tutorial on the OS Dev wiki. So wiki for people who are building operating systems. And go have a look. It's a sufficiently cryptic thing that if you're building an OS, you will understand this long enough to do it, and then you'll probably immediately forget the details. There's also this thing called the interrupt descriptor table. Why haven't I been talking about that? It's both more mundane and also more interesting. People do make attempts to hack the IDT, and you can get into it. You can cause a lot of mischief by hacking the IDT. This basically lets you modify how interrupts are handled by the processor. It's a table of interrupt vectors. So this in here, vector in the sense that the table holds a sequence of 256 addresses. So there are entries. Each entry is 16 bytes in length. You may say, well, wait, an address is only 8 bytes. Fine. Go read the documentation. But you could think of this as just holding, I want to do interrupt 17. So I'll go look at the 17th vector in here, and that will tell me where to find the interrupt handler for it. Okay, the first 32 are for processor. The remaining ones are software interrupts that you can use. And clearly, tinkering with this allows you to do a number of somewhat perverse things, including redirect syscalls. So we don't want you tinkering with the IDT if we can help it. Want to know more? There's a pretty good, not quite complete, but pretty good start on this linked here about how to build an operating system on the x86 family of processors. And it's kind of chatty. It's might be worth taking a look at if you're interested in this sort of stuff. If you're really not, then feel free to ignore that. One of the things you'll probably run into along the way, if you get into this a little more, is the notion of model-specific registers. And these are additional registers on the processor that are often not directly named and are not directly accessed. You have to use some trickery to get access to these registers. And they control a lot of interesting aspects of how the machine functions. If you looked at some of the videos that I linked early on in the class, you may have encountered a fellow who discovered that the Intel chip he was looking at actually had another embedded chip in it, and he could get access to code to run on that chip, and that ran essentially on, underneath the Intel chip, and he could then do anything he wanted to do with it. It's the presentation is called something like God Mode Unlocked, and in there you'll see him make use of model-specific registers. So there is an instruction called CPU ID, and that will let you check to see which specific features your particular processor has. And there's a great deal of variation in all of these processors, right? So there's lots of different versions of the 64-bit AMD 64 architecture out there. Not just AMD chips versus Intel chips, but wide variation within the chips themselves. Some of them are made for specific kinds of applications. And so they may even have instructions that are not present on your garden variety x86. And they may be able to operate in ways that are unusual with respect to the garden variety x86. And the way that you change those operating modes is through model-specific registers. So you use CPU ID to see what processor features you have, and then you can use read model-specific register and write model-specific register to read and write those registers. So those are just the instructions. And you would do this based on the index of the register that you're looking for. And not all indexes are valid, obviously, so you sort of have to know what you're doing. There's a great list of them that I think is hopefully it's been updated, which is linked there. And you'll find some other links to this online. Incomplete collections of the MSRs that people have found and documented are all over the internet, and it'd be great if someone could just take them and fold them all together. So what might you use these for? Well, if you remember the Spectre vulnerability, we actually talked about this briefly. The Spectre vulnerability uses the fact that you're going to speculatively execute some instructions. So I'm doing some operation that takes a long time. And while I'm doing that operation, like I'm accessing memory or doing something like that, I don't want to wait around. And so I'll go ahead and try to do some future work. And I won't know if I need that work until I'm done with the first thing, but I can do what I think needs to be done. And then if I don't need it, I'll throw it away. And we talked about how that could result in a vulnerability. Well, one of the ways that Microsoft, for instance, dealt with the Spectre vulnerability is they made a change to their compiler to modify the contents of a model-specific register to tell the processor to serialize the use of an instruction called lfence. This is getting really into the weeds, I know, just bear with me. So that they change this piece of how the processor operates to make it much harder to exploit the Spectre vulnerability. If you wanted to know Spectre worked on ARM as well. Spectre was not unique to the x86. Lots of processors out there do speculative execution. And if I can use that to access privileged data and then leave a trace behind of that data, then I can exploit this vulnerability. So ARM, for instance, there's something called the CSDB on ARM, and you can look that up if you're curious about how that works. Basically the same kind of thing. All right, just something worth knowing about. Whew. Okay, that was quite a lot. It's 9:32. I'm moving pretty fast, so I'll stop now and say other questions. Super clear stuff. All right, so let's talk about points to analysis. So I originally said Mycroft, but I looked back at my schedule and I changed the order a while back. I want to do Steensgaard first. So we're going to look at a paper by Steensgaard. It's up in iLearn. And if you haven't already grabbed it and taken a look at it, you really should. You should read the paper. So let's talk about, before we get into that, let's talk about pointers and aliases. There's some background information we need to talk about. So over on the right-hand side is a fragment of C code. And hopefully that's like super obvious C code. You look at that and you're like, oh yeah, I do that all the time. And if you do, I have to worry about your sanity because no one should be doing that. But I do have, I may or may not have written code that does this kind of thing. I'm not going to fess up to it if I have. Anyway, over here we have, when you see this kind of thing, we've got parentheses around this thing, you'll know you've got a function pointer. So we're declaring a function pointer f. It takes a char star star and it returns an int. And we have the little question mark colon operator over here. So we look at what's in check. If it evaluates to true, it's non-zero, or it's true, or it's a non-null pointer, then we set f equal to function 1. Otherwise, we set f equal to function 2. Yeah, so this kind of code used to show up a lot more in C code. Now, when you want to do this kind of thing, I would just advise you to write C++ and be done with it. But this certainly can work and does work. Okay, so here, after this happens, f can be either of two functions, right? It's a pointer to something. It can be a pointer to any function that matches that function prototype, right? Takes the char star star and returns an int. And that's checked by the compiler. It's not checked at runtime because it's C, but it is checked by the compiler. C is a statically typed language. And so we would say maybe f is func1 or func2, and hopefully they have the same kind of semantics in a way that's meaningful. For this piece of code right here, I didn't just invent it for this class. I stole this from a program that's out there. Check tells it whether or not to check the contents of the array before performing an action. And this is basically a switch you can apply when you run this piece of server code. And checking the array takes time. So if you want to run the server code much faster, you avoid the check. And the way that it does that is you add this switch, the code that performs this particular operation, it performs a re-indexing of a hash table. It can do it without checking, which is dangerous but very fast. So good stuff out here. I won't say what program this is in. It's in a widely used program. Pointer analysis is the piece of static analysis that we would use to determine which pointers or references can point to a particular thing, like which version of f am I looking at, and what is f, and where does it point and where can it point. That's pointer analysis. Now, I might have the case that I have two different pointers that point to the same storage location. If I do, I call that aliasing, pointer aliasing. And we talked about aliasing in a different context where I had more than one name for parts of a register, right? AX is an alias for the first 16 bits of RAX. Okay. And this is the same basic idea. I have more than one name for the same thing. So why do we need pointer analysis, and why do we need to worry about aliasing? Well, over on the right now is some simple C code, simpler code than we had before. I hope you agree. So I have a thing called pointer, and I go ahead and turn it into an L value with the star. So now I've dereferenced it. So I want to store something in that location. And what I store is the value x plus y. And then the next thing I do is I set z equal to x plus y. And so my question for you is, do I need to compute x plus y more than once? Can I just compute it once, have it in the register, and then store the register in the address pointed to by PTR, and then put the register in and let that register represent z? Can I do that? That's fast and efficient code. Or do I have to compute x plus y a second time after that assignment? And if I get it wrong, you're going to write this code and it's not going to work the way you expect. So the compiler certainly needs to understand this, and it'll turn out that you also need to understand this in order to analyze programs. So do I need to compute it more than once? Maybe I do, maybe I don't. And honestly, I can't tell from the code I'm looking at right here. What if PTR holds the address of some other variable that's involved in this? Let's add some context. So up at the top, you can see that in fact, pointer is actually holds the address of x, so it's really essentially the same as x. And so given that, what I'm doing in that first line is setting x equal to x plus y. And so yeah, I do have to compute x plus y both times. So star pointer and X are the same thing, really. And you might wonder which one is the true value. If I change either one, both of them change. And so why would I ever do that? Would I ever have that in my code? This is super common. This happens all the time. It's a really common thing in code. All right, what about this piece of code? I set X equal to 5. I set whatever P points to 15. And then I compute Y gets X plus 10. And I'm going to ask a little bit different question. And the question is, let's say this is all the code you got. The world ends after that line Y. Is P live? Well, P is not syntactically live because it's not mentioned. This is the secret answer to that question on the exam. It's not syntactically because it's not mentioned anywhere. But it could be that it's actually an alias for something else, and that thing is live, right? X is live because it's used in the last line. So maybe P isn't live, but the contents of it, because it's an alias to X, are. And so we have to think about 3 cases, right? P is the address of X, in which case, yeah, it's definitely live. It can't, if it's the address of Y, we don't care because Y is not live, right? Y is about to be overwritten. So it could be X, in which case it's live. It might not be X, in which case it's not live. Or maybe we can't tell. And if we can't tell, then that's a problem. So we'd like to be able to figure that out so I can answer the question of whether I have to keep track of P or not in order to figure out what the program is doing. Okay. So does this ever happen in assembly? Oh, it happens all the time in assembly. Assembly is replete with examples of aliasing. Got 2 lines of assembly code over on the right that I could easily imagine showing up in a piece of code. I go to a table. I go and I use RSI as an index to pull out an 8-byte value from that table. And I put that in RCX. And then I push RCX. So after those 2 instructions execute, I have the value stored in 3 different places. I have the value still in the table. I have it in RCX, and I have it on top of the stack. And an interesting question is, which one's the real value, right? Because I have it in 3 different places. And if I start then changing those different ones, I have to sort of keep track of which one is value prime, which one is the real value, to be sure that changes get reflected back in the way I want them to. Or I could do a whole bunch of work in a subroutine based on what's on the stack, and then I return. I forget that I did that, and I start using RCX, and I'm wrong, or I don't update the table. And so where should it really be at that point? And which one's the real value? I have to keep track of that. And so I have aliases for it. I have pointers certainly in that code, right? I'm pointing to something in ref table. It's not got a nice name like P, but it has that little name in square brackets. And I've got to think about this stuff. So how do we do this? How do we do pointer analysis? How do we figure out what points to what, or what could point to what? Well, there are 2 different tactics that people have used. And the first one is flow sensitive analysis. And this is maybe the more obvious one. The idea is I'm going to look at my program and I'm going to trace the program flow, and I'm going to see how pointers evolve over time as the program executes. And that has some advantages. It's conceptually simple, but it has a disadvantage that it is also quite complex, and it might not converge, right? We already know that a lot of things about programs are undecidable. So without getting too deeply into this, think about me trying to figure out what a pointer is doing in an arbitrary program in which I'm having a hard time figuring out if a loop terminates, or if a piece of code that modifies a pointer ever runs, or classifying the conditions under which that code runs. So flow sensitive analysis exists. There are algorithms out there that do it. There are modern algorithms that do flow sensitive analysis. But we're going to focus on the one that's over on the right-hand side, which is the flow insensitive analysis. And this says, that program flow that was making stuff hard, we're going to ignore it because it makes stuff hard, which is great. I love it when we do that. We just throw this stuff away, right? It's just too hard to do this stuff. So we ignore program flow and we try to deduce what pointers are being used for in the program by just looking at the program text and not worrying about how control flow impacts it. So this can give us an algorithm that converges. Analyzing programs is still fraught, but we have a much better chance of getting a good result than we do with flow sensitive analysis. Now, programs are weird. Programming is a strange and frustrating activity. Can it be that flow insensitive analysis is always going to magically work for every program? Maybe, right? There's some things being presumed here, like pointers have a specific thing that they address. So in C, I might have a void pointer, and I can point it to anything. And then later on, I can cast it back to whatever I need it to be in order to dereference it. So if I'm doing flow insensitive analysis and I expect the pointer to have a sort of fixed type, I'm out of luck. All I can really say is, you know what? It points to something, and that's maybe the best I can do. With flow sensitive analysis, I can say in this portion of the program, it points to a string, and in this portion, it points to this particular struct. So there are strengths and weaknesses to these different approaches, and they're harder or easier, as the case may be. The one that has won out in nearly every application I'm aware of is flow insensitive, because it just gets you out of this morass of trying to compute the incomputable. Right. Two important algorithms for it. One of them is of historic importance, and that's Anderson's algorithm. The other one is of current relevant importance, and that's Steensgaard's algorithm. And I would say that almost any flow insensitive analysis, pretty much any points to analysis that you're going to find out there in a program like Ghidra or in a variety of other tools, is going to be using maybe a modified version of Steensgaard's algorithm. It's a really significant algorithm in computer science. And it's the subject of the paper that's up there, which again, you should read. And you may find the paper a little hard, so we're going to try to go through some parts of that to make it maybe easier to process. But let's first talk about what Steensgaard's algorithm is and why it might be a good thing. So Steensgaard's paper is titled Points to Analysis in Almost Linear Time. That sounds great. Almost linear sounds great. Almost linear, if David Parnas were here, he'd point out that the word almost means not. So it's really points to analysis not in linear time. Well, it's going to be close to linear time, and that's going to be pretty good. Whenever you see someone say linear time or whatever, you need to ask with respect to what, right? What is the n in your order of n, right? I mean, is that something simple? And in this case, it is. It's basically lines of code. So the idea is this will scale really well as your program gets big. Flow sensitive analysis scales terribly as your program becomes more complex, right? As the cyclomatic complexity, we haven't talked about that, but just imagine that as a way of measuring how much spaghetti code you have. As that goes up, flow analysis becomes intractable. It goes up really fast. And I think it's like factorial, something like that. Well, this goes up almost linearly, not quite, but almost. And we'll find out why it's almost. In terms of the length of your program, and that's great. That's something we can easily measure. Length of program is pretty easily measured. Cyclomatic complexity, less so. So that's good. And Bjorn Steensgaard was at Microsoft Research. I forget where he is now. I don't think he's there now. I have to go on and look. So it's flow insensitive. That's a good thing. It means we don't care about flow control structures like loops and branching. That's nice. Interprocedural. This basically is a fancy word that says we're going to analyze your whole program. Your program may be a collection of procedures that where control flow transfers among these procedures to do work, right? I call printf. That's a procedure that I call. Well, this is going to take all into account. It's interprocedural. It does points to analysis. That's great. It solves the problem we care about, which is the points to problem. Hooray. It needs linear space. You weren't thinking about space, right? The algorithm runs in linear and almost linear time. Fortunately, it only needs linear space. That's good. So it's not got a pathological case where it takes over your machine. And it has almost linear time complexity. So that's theoretically fast, but it's also very fast in practice. So that's even better. Okay, so that's my bullet summary of his abstract. Linear here, again, means with respect to the length of the program, essentially the number of lines of code. And of course, it's also actually fast. We like that. So in Steensgaard's paper, he does not use an existing program language as such. He uses what might be thought of as a PL1 or C type language. He invents his own little toy language in order to excuse me, in order to express the ideas. And that's not that uncommon or weird. It's just he needs to have a language to express this. And so let's take a look at his little language. So over on the right-hand side is the BNF for statements. I'm assuming everyone knows what Beckers-Nauer form is and has read this kind of stuff before. And so it's a little imperative language. Imperative meaning it changes, it makes persistent changes to stored data. And that's significant as opposed to a functional language where we compute functions over fixed data. So little imperative language, and the language has pointers to locations. It has pointers to functions. That's good, right? We don't want to use a language that doesn't have pointers. How would we do points to analysis if our language didn't have pointers? So he has pointers, great. Pointers to locations and pointers to functions. He has dynamic allocation, and he has the ability to compute addresses of variables, take their addresses. All good stuff. We don't care about flow structures. And so just throw in whatever flow structures you like. Don't get worked up about it. If you need an if, just throw an if then else, or whatever you want in there. If you need a while loop, throw a while loop in there. Don't care. We're not going to worry about that. So if you see, oh, he's using a while loop here, but he didn't tell me the semantics of his while, doesn't matter. Don't care. Okay. So basically, he's giving you pseudocode, but you should be able to see how to translate that into a language like C. So variables in his little language are assumed to have unique names, so we don't have this weird cross-procedural alias problem, right? So printf has a variable called I, and your code has a variable called I, and Sterling has a variable called I, and they all mean different things, and that would be a problem. So let's assume that we resolve that somehow. Maybe it's printf.i and mycode.i and sterling.i. I don't care. However we do it, whatever name mangling system we come up with, we're going to assume that variables all have unique names. We're going to have the usual address of operator. We put an ampersand in front of a variable that takes this address. It gives us back a pointer to the storage location of that variable. Only going to work for things that actually have storage. As you already know from C, you can't stick this in front of things that are transients that don't have allocated storage. Doesn't work. We can dereference to obtain an R value. So if Y is a pointer, I can stick an asterisk in front of it, and go and get the contents of the location pointed to by y, interpreting it according to y's type, and then placing that in as an R value. Op, in this case, we have this x equal op of all these variable, all these arguments. This is just any primitive operation. So then later on, he can say x plus y. And you're like, well, you didn't give us x plus y in here. Well, he gave you any operation. He has dereferencing for an L value, different operation, right? So if I put the asterisk in front of x, x is location, and now I'm saying I want to store the result of the computation on the right of the equal, whatever the R values end up being, in the location pointed to by x. So dereferencing to obtain an L value, a place where I can store things. Declaring functions. So this is how he declares a function. He says x equals fun, and he gives you the arguments, and he gives you an arrow, and he gives you the returns, and that's it. And that's followed, if you look over here, you'll see this weird S star. What is S star? That's the clean closure of S. And it probably should be a plus, but it's a star. That's why he has it in this paper. And that's these statements. So it's this fun declaration followed by some statements that make up the function. Pretty simple. How do things get to be arguments or returns? They're positional, right? So F1 is the first argument, etc. The value assigned to R1 becomes the first return. And he allows you to have multiple return values. And then finally, you can invoke the function you declared earlier. So here we invoke the function P with some arguments, and then the return values are over here and can be assigned all in one smash using equals. And that's basically his little language. And so what does a program in that language look like? Well, it looks like what's over on the left. So here he says fact equal fun x, and the return is R. That's this little line right here. We expect that to be followed by a sequence of statements. And in fact, it is followed by a sequence of statements. And he didn't mention if or else. And he didn't say phi anywhere. It's fine. We know how if then else's work. So what about less? He didn't mention less than anywhere. Less than x and 1. That's just applying an operator. And he's going to use spaces here. I don't know why. Could be a Steensgaardism. Who knows? So if x is less than 1, then R is 1. That's our return value. Otherwise, we do some stuff, and R is the result of that. And if you squint at this, you'll see it's just doing the factorial, right? If I come in with x and it's less than 1, then the factorial is 1. No one ever wants to use the delta function. X minus 1, I just take x and subtract 1. The next factorial is the factorial of x minus 1. So I'm able to recursively call my function. And once I have the next factorial and I have x, I multiply those to obtain the complete result and return that as R. And I might invoke it like this. The result is the factorial of 10, so 10 times 9, etc. And so this is what a little program in Steensgaard's language looks like. These are the important pieces. Now, Steensgaard is going to spend a lot of time talking about types, and he may do it in a way that is somewhat unfamiliar. So let's spend a little bit of time looking at that. Actually, before I get into this, let me stop for a minute and say, are there questions about this so far? I feel like I'm going really fast. Sorry if that's the case. I want to get through this, and I have to get to the lab. All right. If you have questions, just feel free to chat out and stop me. So we need types for the language. We have all the little statements, but we're also going to need types. The types are important because they're going to tell us something about memory shapes. We haven't talked about memory shapes, and there's a whole additional piece of analysis called shape analysis that if we have time, maybe we'll get to do some of that. But we need to know, right? Are you pointing to an int? Are you pointing to a structure? Are you pointing to a function? Are you pointing to another pointer? Right? So we need to know something about what's being pointed to and what's stored. in order to figure out what's happening. And that's actually going to be crucial to running Steensgaard's algorithm. And so he gives us what's over on the right-hand side. And that should not necessarily look obvious to you in any way. Tau is the type of a thing that's being pointed to. So if you have a composite like a struct, and he has structs in his language, this is still just that single thing, right? It's the type of that struct. And so that's what tau represents here, just a type of a thing that's being pointed to. He goes into some depth about this. He says, if I were to describe each element in a composite object by separate types, then that would have implications about the size of the storage, shape, etc. I could use type def and other things, and he wanders on about that. And basically what he comes to is, I don't want to do all that. I don't want to tell you how to define the types of complicated data structures. So I'm just going to say, if you need to extend the type system to do that, go do it. Depends on your language and what problem you're trying to solve. And so go do that, but I'm not going to do that here. That's a fancy way of saying I'm leaving that as an exercise for the reader. So there you go. Lambda is the type of a function invocation. And if you're a functional programming person, that choice will probably make a lot of sense to you. But, oh, lambda, of course it's for function types. And you'll see that it depends on things like the types of the arguments and the types of the returns. So two functions that differ only in the type of thing returned would be different function types. And two functions that differ only in the type of an argument would be different function types. But if they agree on all of those, they're the same function type, at least according to the type system he's setting up. One thing you might notice in here is this funny little symbol. This must mean that things are perpendicular. Sure, that's what it means. That is the bottom type. Sometimes we refer to that as simply bot. And it's the bottom of the type lattice. Type lattice. So I build higher level types like structs and databases and the World Wide Web, etc., out of more primitive things, right? I build them out of ints, right? And eventually out of bytes. And so I could think of this lattice where I have these primitive things at the bottom, and then I build up more complicated types out of them, and I work my way up in this type lattice. So don't get too hung up on that. Just think of this as the case that something is a non-pointer. Okay, that's the easiest way to think about it in terms of understanding this paper. I will mention an aside, type theory is, depending upon what kind of person you are, it can be really fascinating. I think it's pretty neat stuff, but maybe I'm just weird. There's something called the Curry-Howard correspondence. Another very famous piece of computing theory. Many of you may already be fully aware of it. If you're not, you might Google it. This is not intended to be a joke. I'm not sending you off to read, deeply abstruse mathematics. It's kind of a neat result. Basically, it says programs are rules for mathematical functions, and it's the basis of a lot of the formalization of computing theory. It's neat stuff, and I'd recommend you go take a look at it. Curry is a fairly famous person. If you've ever done anything with lambda calculus and you're currying functions in lambda calculus, that's the guy. That's Curry. He did not invent various cuisines. Someone thought, I kid you not, someone was once like, well, did he have anything to do with curry, the food? I'm like, no. So don't assume that, please. I can't have to say that, but I'll say it anyway. But he does have to do with a lot of interesting results in computing theory, especially in the formalization of it. What's alpha? Alpha is simply a value. It might be a location, or it could be a pointer to a location, or it could be a function, or it could be a pointer to a function. Really? Absolutely. So take a look at this, right? It's going to be, back up, it's going to be tau cross lambda. So looks like an ordered pair. Tau is going to be a concrete thing or a reference to something. Lambda is going to be a concrete function, or it's going to be a reference to something. So we're going to catch them that way. Notice that we do have alpha showing up over in these other expressions. It's recursive types are absolutely allowed in Steensgaard's world. So alpha could be tau, which has a reference to an alpha, a different alpha, which could also have a reference to it, and so on until eventually you terminate it by choosing the basis case, which is bottom for each one of these, and terminating the recursion. In addition, we can have type variables, right? Basically, alpha is a type variable. And we need those so that we can write down recursive types. Otherwise, we would be in trouble, right? We'd want to be able to say something like this. We have to fill this in with all of this stuff again and again and again. We don't want to do that. So we just stick a type variable in here, so we can refer to it later. Nothing magical about that. It's just a statement that Steensgaard makes in the paper, and I thought I'd point that out here. Let's see, when we last stopped, we were talking about we just finished talking about the type stuff in the Steensgaard paper. And so for his source language, he wants to be able to give types for the program. And so he has a set of typing rules that will tell you when and whether a program is well typed. So what does it mean for a program to be well typed? And he tells you this: a well-typed program is one for which the static storage shape graph. What's a storage shape graph? Well, that's all of the different pieces of storage and how they point to one another. So a linked list, you picture a linked list in your head with the little pointers pointing to the next element, you're looking at a storage shape graph. If you think about a tree, again, you're picturing in your head the storage shape graph. So nothing too foreign or strange here. But it should be static, a static storage shape graph indicated by the types. And we want that to be a safe, and he says conservative, description of all possible dynamic storage configurations. So what does that mean? So what he's saying is, no matter what the program ends up eventually doing at runtime, what I have now with the types I've assigned is going to still be true, right? So I've got a set of static assignments of types to things, and that's going to be true pretty much irrespective of what the program ends up actually doing when I run it, right? If I said this is a pointer to the root of the tree, that's always going to be a pointer to the root of the tree. And if each element has a pointer to, let's say, a left and a right element, and maybe a pointer to some data, that's always going to be true as the program runs. And so my question for you is to think about is this actually always possible? All right. And that gets to the question, are all programs well typed? And what would that mean in practical terms? Well, I've already given you the case of, well, I have these void pointers and they might point to different things at different times. Well, maybe that's okay. Maybe I can say, you know what? It's a void pointer. And that's my static type for it, and life is good. But, it's worth thinking about, because this whole enterprise that Steensgaard is cooking up depends on this static storage shape graph existing and being a well-typed representation of the program. And so this can imply limits on what he's doing. So give that some thought. The typing rules are given as inequalities. So what this means is they constrain, but don't necessarily determine the types. And Steensgaard is going to go to great pains to not over-determine the typing of things in the language. Okay. Let's talk about schemas, because schemas, in the mathematical sense, show up in Steensgaard's paper, and you should be familiar with the basic structure. So here's an argument schema. This basically constitutes a logical argument. Up on the top, I have a database of statements that I assume are true, or I believe to be true, or that I have previously proven to be true, or that you and I agree are true, right? All men are mortal, and Socrates is a man, right? The schema doesn't tell me these absolutely are true statements. It says you get to assume these, okay? And if it turns out they are true, then you get to also accept the conclusion. You are obligated to accept the conclusion, right? If the premises are true and this schema is a correctly constructed argument, then you are obligated to accept the conclusion. Okay, so Socrates is mortal. Big what? Two classic examples of this are modus ponens, which is a fancy way of saying the mode that affirms, and modus tollens, which is the mode that denies. And over here, I have two premises up here. I say, I know P is true. I just assert P. So I just do it like this. What I'm saying is P is true. I also know that whenever P is true, it is also the case that Q is true. And since I know that P is true, and I know that whenever P is true, Q is true, I can therefore logically conclude that Q must be true. Over here, a little bit different. I know that Q is not true. And I know that it's the case that whenever P is true, it is also the case that Q is true. And I know that Q is not true, therefore I can conclude that P is not true. Okay, two classical examples of this. Just examples of argument schemas. Another thing you're going to see in his paper is this. You're going to see this funny little symbol here. And you might see it in this context where he says this little symbol and some statement. And what this is saying is, I am asserting that Q is true. Q is true. And what am I basing that on? In this case, it's an axiom. It just is. The little thing in front of it is the logical turnstile. We can, if you want to say it out loud, instead of saying logical turnstile, that makes you feel weird, just say entails. So it represents entailment. It typically, like everything, it gets misused in a variety of ways in different contexts, but normally it represents provability or derivability, right? I have done some work, and from that work, I can conclude that Q is true. Or I've done some work, and that work resulted in Q being true, right? I proved it or I derived it. And so I know Q in this case to be true. I might have something over on the other side of it, right? So P entails Q. And that might sound like implication, but it's not quite the same. It's a different kind of thought, right? I can derive Q from P, or I can prove Q based on the set of facts that I over here in P. Okay, I know Q is true because I know P. Whew. All right, that got us through, I think, everything that we have to know for right now about that. Let's talk about some of the typing rules that Steensgaard throws at you in his paper. So first, he proposes this rule. And we already pulled apart some of the pieces of this, but what we see here is we see a schema, right? We see up here a set of things that that if these premises hold, then I'm obligated to conclude the thing here on the bottom. And we see the little logical turnstile, but we also see this colon here. I didn't mention that. That's typing. So we have a typing rule called A. So Steensgaard says, imagine that I have a method that assigns types to variables in your program, or types to names. I guess I should say names because functions can also have types. So I have a rule that assigns types to names. That rule is called A. So here I say the typing rule A leads me to conclude that X has the type reference to alpha. It also leads me to conclude that the name Y has the type reference to alpha. Both X and Y under my typing rule A have type reference to alpha. Therefore, I conclude that A is well typed for X equals Y. Okay. In other words, the expression X equal Y is well typed, whatever that means. I'm defining it here under the typing rule A, if those two things up here are true, right? If this, then this. And it kind of makes sense, right? I mean, both X and Y refer to a type of alpha. And so setting X equal to Y, this is assignment, that he concludes that that's well typed. Great. So given the typing rule A, I can derive that X has type ref alpha and Y has type ref alpha. And then I conclude that the typing rule correctly types the expression X equal Y. Great. That all seems perfectly reasonable. It's so reasonable, in fact, that Steensgaard says it's unreasonable. He says this rule is too strict. And what does he mean? Well, what he means is this forces us to assume too much. Suppose X and Y hold pointers to different locations. We require that the data at those locations be the same type. That's what that's doing here. It's doing a lot of work. But do I have to do that? I could say X gets Y as long as Y will properly be able to be assigned to X. And in a world like C++ and other places, it might not be that these things have to have exactly the same type, right? Y might be a cow or a chicken or a dog or an axolotl, and X could just be anything that's allowed to hold an animal. And there you go. So he says this makes us assume too much. I want a more relaxed rule. I want to say I can assign Y to X if the contents of X and Y are compatible in a sense that X might contain Y. Well, I have a way of expressing that in here, so I'm going to have to introduce more math. Always use more math, and in fact, he's going to throw some more at us. So he goes ahead and defines a partial order. Now, you probably all had discrete math, and so you know what a partial order is, and so don't get mad at me for re-explaining it. Just in case you've forgotten or need to be reminded, a partial order is a relation, right? So in this case, the partial order has this funny little symbol here that looks deceptively like a less than or equal, but isn't exactly less than or equal, right? This is his containment relation. It's going to be a subset of some set A cross A, right? Some relation, such that it's a partial order. And what does that mean? That means it's reflexive. So if I have a y in here. Y is related to y by this, right? Y is, I'm going to use less than or equal because that's just makes sense to me. Y is less than or equal to y, right? 5 is less than or equal to 5. Makes sense. It's reflexive. That's true. So every point in here, I can put it on both sides of this, and that's true. It's in the relation. It's anti-symmetric, meaning that if I can't have y is less than or equal to z unless, and also z is less than or equal to y unless y and z are the same thing, right? There's a directionality implied, and it's transitive. So if x is less than or equal to y and y is less than or equal to z, I can conclude that x is less than or equal to z. Okay. So a partial order relates elements of some set, but not necessarily all elements, if the relation is defined for all the elements in its total order. So an example of that is over here. And this is a common example of a partial order. It's the subset order. So up here at the top, I have x, y, and z. And down here, I have all the 2-element subsets of x, y, and z. Down here, I have the single element subsets of x, y. And then the empty set is a subset of every set. So it's certainly the case that if I use the subset relation right here, x is a subset of x. Okay, so it's reflexive. If x is a subset of xy and they are not equal, then I don't get to conclude that xy is a subset of x. That can't be true. That's anti-symmetric. And if x is a subset of xy and xy is a subset of xyz, then x is also a subset of xyz. That's the transitive rule. I'm not showing those additional lines here. I'm showing something called, well, we won't get into that. I'm showing a cover, but don't worry about it. Don't worry about that piece of it. This comes off of our friends at Wikipedia. It's a pretty good little graphic. If, in fact, I could relate everything to everything, I would have a total order, but I can't do that. How do these two relate? Is y a subset of x, or is x a subset of y? Well, neither of those is true. So there's no arrow in either direction here. So it's not a total order because a total order would have to relate these two. But we don't relate them with subsets, so it's a partial order. All right, so he comes along and he wants to define a partial order among types. Okay, let's see if we can understand how he does this. I've got to leave very soon, so I hope I'm close to the end. We'll say that type 1 is less than or equal to type 2 if and only if type 1 is bottom. So the first case is this could be bottom, and then the whole thing is true. Or they're the same. Okay. So what can types be? Well, they can be primitive things like bottom, or they can be like references to things. So they have to be the same thing, or this thing over here is allowed to be a primitive thing like bottom. Either of those. Down here, we have something that deals with the cross of two types. And that's important because remember, that's how we actually defined alpha. And so we say that this is less than or equal to this if and only if type 1 is less than or equal to type 3 and type 2 is less than or equal to type 4. So there we go, and there we go. This is the usual notion that you see of covariant types. Okay, and we point out that we can generalize this to any sequence because of recursive types, right? Each of these types could themselves be a cross product or something else, and we expand this to infinitely long sequences, and we would expand this side, we'd expand this side accordingly, and we get the proper rule for that. So this really defines all those cases. But they have to have the same length. If they don't have the same length, if this is just T1 and this is across, it won't work, right? Because I haven't defined that. It's a partial order. It doesn't tell me everything. It just tells me something about some of these. You can think of this, at least I find it's helpful to think of this as T1 will fit in T2. So now he says, now finally I can give you a good typing rule for the assignment of the value y to x. And it looks almost the same as it did before, but you'll see he's made a change. This is alpha 1 and this is alpha 2, so they could be the same, but they're not necessarily the same. He gives you a third thing which constrains those values, and it says alpha 2 has to fit in alpha 1. Does that make sense? Alpha 2 is the type of the thing pointed to by y, and that has to fit in the type of the thing pointed to by alpha 1. Makes sense to me. Okay, great. Then, and only then, can I conclude this is well typed. Great. So that's his good rule for typing the assignment statement. Took a while to get there, and we got through one. In the paper, there are going to be some others. Okay. Hopefully this stuff at the bottom will help you make sense of it. All right. And now what he does is he goes back and he types all the things. So remember at the beginning, we had that little S equal, and we had all the different types of statements in his language. Well, here they are. You see assignment. You see taking the address of y. You see turning a pointer into an R value. You see applying an operator. You see allocating some memory. You see turning a pointer into an L value. You see defining a function, and you see applying a function. And for each of those, he gives you a type rule in pretty much the same way. We went through this one in gory detail. The rest of them are actually, honestly, somewhat simpler. This one looks really ugly, but I think you can work through this one and see that it makes some sense, right? It's mainly to do with matching up the types of the arguments and the returns and making sure that it all works and that they all fit into the appropriate slots. So here are his rules for a typing rule. Remember, this is a little bit abstract, but all of these mention A. A is the typing rule that assigns types to names. And we're talking about when that's well typed, when we can accept that typing rule. And if all these hold, we get to accept A as a valid typing rule that tells us the types of things. But any rule that does this will work. So we're constraining it. We're not totally determining it. Okay. Whew. With all that out of the way, we can finally turn to the central claim of Steensgaard's paper. And the central claim is this: the task of doing points-to analysis has been reduced to the task of inferring a typing environment under which a program is well typed. So he says, I have taken this hard problem of pointer analysis and I've turned it into type theory. And if you can give me a rule that tells me the type for everything in your program, you have actually solved the point-to problem. More precisely, the typing environment we seek is the minimal solution to the well-typedness problem. The minimal solution. Each location type variable in the typing environment describes as few locations as possible. We do the best we can do to define these, right? One solution is I tell you anything can point to anything. That's not a helpful answer. That doesn't solve the typing problem. I tell you A points to an integer. That's helpful. I tell you B points to something. Maybe that's the best I can do. But if I can do better than that, well, then I should. I tell you B points to either F or G. That's okay. if that's the best I can do. So this is what his central claim is, that I've turned the points to problem into type theory. All you've got to do is assign types to your program, and you're good to go. And you don't have to worry about, because of the way I'm structuring this, you don't have to worry about loops and branching, etc. We're not going to look at the algorithm this time. I'm going to save that for next time because I am out of time to talk about this. But let's quickly talk about the homework, and you're going to have lots of questions about the homework, and email me those questions. So you will have questions. Please email me about them. We're going back into Python, back into Capstone. You haven't looked at this for a while, so it may be a little jarring. So the thing you're going to do now is you're going to find main. So given an unknown program, if we assume that libc start main is going to be called, then we should expect RDI to hold the address of main at that point. And you can go back in previous lectures and see why that's the case. We want to use this to write code that will find main for us. And that's fairly important. Usually when you're analyzing a program, finding main is one of the first and most important things you want to do. It's not always obvious. So your task is to write code that does the following. I give you an ELF binary executable. You'll find the entry point. You'll disassemble the basic block that starts at that address, and you'll look for a pattern. You'll look for a call followed by a halt. That's typically what these things are going to output. Are there variations in this? There are, but for the purpose of this assignment, we're not going to worry about that. You're going to look for a call followed by a halt. We're going to make the assumption that call is to libc start main. How would we verify that? Well, we can think about that. But for the purpose of this assignment, we're going to make that assumption and move on. You're going to figure out the address that's stored in RDI. Now, this can be tricky because that address is going to be given fairly explicitly, but it'll be given in one of two different ways. It might be an absolute address. It's like, put this value in RDI. And you absolutely will see that in some programs on the system. The other thing you might see is RIP relative addressing. In that case, you have this task of figuring out, okay, what's RIP and what's the offset, adding those together, and that being the location of main. Okay. When RIP relative addressing is used, you only have RIP and a fixed offset. You don't have an index. You don't have like you can't have RIP plus RCX times 8, right? It's always RIP plus a fixed offset. That's just how that works. So you'll then print that out in hexadecimal. If you can't do any of this for some reason, right? If you can't find the call followed by a halt, or you don't find anything that's assigning RDI, you'll just tell me you can't locate main. You'll call your program main.py, and how it looks when you run it should be what you see over on the right-hand side. So run it on LS. On my Ubuntu system on this laptop, I get 4E00. When I run it on the dynamic loader, it tells me it can't locate main. So that's your assignment. It's due in a week. You'll undoubtedly have questions about them. Email me and ask those questions, and I'll try to get back to you. Some hints. Don't try to parse the text. You've got a library. The library actually has stuff in it that will let you pull apart these instructions and get the operands and do some other stuff. So pull up the library, hop into Python, play around with it, figure out how that works. The documentation for the Python side of Capstone that's online is not ideal, but the documentation for it in the Python code itself is fairly good. Registers will come to you as numbers, and there is a function that converts those numbers into the register names. I think I mentioned that previously, but you can go and find that. Shouldn't be too complicated. Some helpful assumptions. We're going to assume that if you see call halt, that's what you're looking for. That's going to be calling libc start main. That's a big assumption, but it's a not unreasonable one for most of what's on your system. We're going to assume the instructions that you want will be in the .text section. They don't have to be, as we already know, but that's what we're going to assume. And so if you don't find a .text section, or you don't find what you're looking for in the .text section, give up. But make sure you handle errors gracefully. If the file I give you is not found, give me an error. If it's not an ELF file, give me an error. If there's no text section, give me an error, etc. Okay, and use the error library that I gave you to do that, so my automatic checker doesn't complain. And that's it. And so next time we'll continue with Steensgaard. We'll actually begin to dive into his algorithm for doing this stuff and merging types, etc. And that'll be that.